Hi everyone, in this second video on work problems, we're going to look at lifting or pumping liquids. And I've got an example a little bit marked up that I've got here. In this case, it's a cylindrical tank where we have some liquid in it. It might be water or whatever it might be. We want to know how much work is going to be done to, or required to be done to pump it all out. So we want to pump it out over the side, and that's what we're going to be doing in a lot of these problems. Now, there's some simplifications that we need to make when we think about doing this. It's not stated for every problem, but we're going to be kind of assuming that the pipe or whatever we're putting in there to pump it out, the hose, that the pump is floating at the top or is remaining at the top of the liquid line so that we can layer this out and think about pulling or lifting, pumping or lifting the the upper layer out, or whatever, at each partition point, we have to lift that over the side, and that depends on how far up or down we need to lift it and the size of that slice. All right, so we got this figure here. Again, I used some AI to generate this, and it didn't quite label it exactly how I wanted it to go, so I'm just going to mark this up a little bit. Oftentimes, we're going to put the bottom of our figure to represent x equals 0, with our x-axis going up and down through the center of that. And if the total height in this figure is h, again, I'm using a cone in this example, but it's going to be varying shapes that we're going to see here, that would have some radius r, height h, then the height that needs to be pumped out here is going to oftentimes be h minus x of k. And what we're going to be thinking about doing is partitioning up this interval, our x-axis, into subintervals. All right, so we got kind of a similar picture. Again, it's not perfect here, but we've got this radius, so we'll need to think about for cone type problems. All right, delta x is going to, in this case, represent the thickness of that slice, and we have to move it a certain amount. Again, my picture's not perfect here, but we'll see the idea in the example. But one big difference between this and the previous recording, where we're working on problems where we're lifting with ropes or cables, is when we partition this x-axis up into subintervals, we can think about separating out or layering the slices of liquid to lift over. Okay, so let's look at the general setup, and then we're going to do one example in this recording. All right, so the general setup for pumping liquids, we can think about these problems as being partitioned in disjoint layers and determine how much work is required to lift each layer independently of the other one. Whereas when we're lifting with a rope or a cable, everything is connected together. If we're assuming we're pumping off the top, we can take off layer by layer and work our way to the bottom. So that's going to depend on a couple of things, right? How high the layer must be lifted, and then also on its volume. So if we let W sub k represent the work required to lift the kth layer, then as we've had before, it's the force times the distance. The force is going to represent the weight of the kth layer, and the d sub k is representing is just the distance. Now, again, different from that, the um, the distance in this case is not delta x. Right? Again, going back up to the figure, delta x is going to represent the thickness, oftentimes, of the kth slice. So that is going to come into a different area of this Riemann sum that we're setting up. The distance that we're lifting, as we had in the picture above, is oftentimes going to be your height minus x sub k. Right? It's not going to be that perfectly for every problem. It's going to vary problem by problem, so we have to understand this process to set it up. For the weight, which is going to be the force, all right, if we're given the weight density, then we're just going to compute the volume times the weight density. We'll see that in an example below. We might have to go to more basic principles if we're not given the weight density, but we're given, so if we're not given that, but we're given the mass of the liquid, then we can compute the force required to lift that layer by using Newton's second law. Right? So Newton's second law says that force is equal to mass times acceleration. In this case, we're trying to overcome gravity, which is often denoted in physics by g. Now, density is mass divided by volume. If we solve this for mass, we get that the mass is equal to the density times the volume, which is what I'm using in this line right here. So we're replacing the mass by the density of your liquid, and then it's times V sub K, where I'm representing that as the volume of the case slab or slice that we're lifting over. Or it's the volume of the case layer. Again, G is going to be the acceleration due to gravity. If we're talking about this in the metric system, then we're going to use 9.8 meters per second squared. Some problems might want to do 9.81. Okay, if we're in the English system, then we're going to use whatever that is. It's often going to be 16 feet per second squared. Okay, we can look that up or be given the problem. Most of the problems we're going to see are going to be in metric. All right, so for the volume calculation, what that's going to look like and where delta X is going to come up in a different place here is that volume. All right, let's go back up to our picture and we'll come back to that and then get to the example. But if I go up here, the volume, if we think about that as a layer, it's not varying very much in here. So it's going to really be the area, which in this case is a circle in the figure, times the height, which is the thickness, delta X. So most of the problems we're going to see, the volume is going to be the area of the kth layer times delta X. And that's where delta X is going to come out in this problem. So notice delta X is going to be part of the force for these lifting liquid problems, not part of the distance. The distance is going to be something involving X, the variable X or whatever variable you're using. A lot of times it'll be the height minus X sub K. All right, and your force is going to, depending on what you're given, if you're given the weight density or if you're not, then you might have to go for more basic principles here. Delta X does, as we're seeing in here, show up. It just shows up in kind of as a different order as a factor as it did for the lifting with cables or ropes. So as we take limits, we still get a definite integral. All right, again, the delta X is becoming the dx part of it. The rest of the stuff is representing the force, but happens in a little different manner. Okay, so let's take a look at an example here. We've got a cylindrical tank of radius 5 feet and radius 5 feet and height 9 feet. It's 2/3 full of water, which has a weight density. So notice we're not given, we're given the weight density here. We're not given the mass we're not given the density of the liquid. We're given the weight density of the liquid, which weight density is the density times, the weight density is the density times the acceleration due to gravity. So going back up from before, we had mass times acceleration due to gravity, which is g. If we put in density times the volume times acceleration due to gravity and just rearrange these factors, we get density times acceleration due to gravity. That's the weight density times the volume that we're going to be obtaining. All right, so find the work required to pump or lift all the water over the above rim. And again, it's 2/3 full. If you take 2/3 full of 9, so this whole thing is going to be 9. It's 2/3 full, so we've got it to be 6 feet. All right, so the total height in this case is 9 feet. Again, we're representing this is our x-axis. We're going to take the ground or the bottom of this as x equals 0. And what we want to know is if we partition this up, if we partition this x-axis and we're thinking about this representing the kth layer, I'm just going to draw what that layer is going to look like. Get the idea for it in this case, though the thickness of this, the height of this is going to be delta X, and we got to write out that total volume. It's going to be the area, which we can see in this case is a circle, times that height, which is delta X. Right now, if we're thinking about this representing X sub K, and x sub k plus 1. How far are we lifting it in this case? To get that kth layer out, we've got to go from the top, which is at a height of 9 feet, x equals 9, minus x sub k. That's how far or what height we need to lift it out at. All right, so let's use all this figure and this notion to set up the integral. All right, so it's going to be, again, force times distance. The distance the kth layer is going to be lifted up. Let's put that in. It's going to be, in this case, 9 minus x sub k. The weight of the kth layer, that's going to be the weight density times the volume. In the problem, just scroll back up for a moment. We're told that the weight density, notice we're given imperial units here, is 62.4 pounds per cubic foot. All right, so let's write that out. It's going to be, in this case, weight density 62.4. I'm going to subtract the units, pounds per cubic foot. We've got to write out that volume. The volume is going to be the area, which is going to be pi r squared, times the thickness, which we know is delta x. The radius was given to be, for us in this problem, 5 feet. So we're just going to put 5 feet in here. Notice the units on delta x are also feet. We think about just simplifying that expression out. We'll square the 5. We get 25 pi times delta x times our 64 or 62.4, excuse me. But then we're going to have times 25 pi times delta x. Just tracking the units kind of off to the side over here. Pulling the units over, we would have pounds per cubic foot times feet cubed. Those feet cubed will cancel. We'll have pounds, which is what it should be for the units for force. All right, so now getting down to building this up. Our force was 62.4 times 25 pi times delta x. Our distance that we're moving it is 9 minus delta x. All right, just for time's sake for the recording, I simplified that and wrote it down below. So what I do is multiply the 62.4 times 25, and that gives you 1560. We still have pi in there times delta x times 9 minus x sub k. Taking limits, we're going to end up with our definite integral, and we're going to integrate this from 0 to 6 only, not 0 to 9, because the tank was 2/3 full, and our integrand becomes 1560 pi times 9 minus x, and remember the delta x is becoming the dx. All right, and just for time's sake, we're not going to work through this whole calculation, but I believe it comes out to 15,560 pi, and then the units on here are going to be foot-pounds. Okay, I got a correction there. I copied this down wrong. I've had this worked out. It comes out to 56,000, 160 pi foot-pounds. And that's what that integral will come out to, as we could check. All right, so that's it for this problem. And again, just to notice some of the highlights we have here. Again, getting the integral down is the important part. We have to set up the Riemann sum and then take limits to get that definite integral. Usually that, in this case, is not going to be very hard to write the antiderivative down, use the fundamental dynamic calculus to work it out. But notice the difference in how this was determined comparing to the last recording, last video on lifting with ropes or cables. Delta x is not the distance. Delta x is part of the volume calculation. All right, but we still do end up with that as part of our Riemann sum, and therefore, taking limits, we can get a definite integral.